So it's really great to be here. I'm also really glad that you're not in Boston today. So, although my flight's already been canceled for leaving tomorrow, so maybe I'll be here a little longer than I was expecting. So this is, I'm going to be talking about some work that was done at Rice University. This is a picture of the old part of campus. This is our old physics building, built about 100 years ago. And every 100 years at Rice, we get a new physics building, I guess. This picture's small. This is our new building. And since 2011, we've been in this new building, and we love it. It looks a lot like your new building in many respects. And the wait is worth it. I know it's going to take you guys a little longer, but it really is nice. So I'm going to be talking about quantum degenerate atoms. And as we all know, there are differences between bosons and fermions. This is a kind of a proverbial harmonic confinement potential. Bosons on the left, fermions on the right. Lithium happens to have stable isotopes of both bosonic and fermionic isotopes. The only difference is that lithium-7 has one additional neutron. And because of that one additional spin-and-a-half particle, that means that there is, oh, I don't have the little microphone thing, so I'm supposed to use that. I promised that I would. I'm sorry. I just realized looking back out there. All right, am I on your? Good. All right. Sorry about that. That one additional neutron makes all the difference. So at zero temperature in this harmonic potential, bosons will both condense, and they'll all occupy at the lowest temperature, they'll occupy the lowest energy level of the confining potential. And fermions, in the case of fermions, because of the Pauli principle, this is all non-interacting single component particles. There's only one particle allowed per energy level up to the Fermi energy. And of course, these differences can have profound implications. This is an experiment that we did. It's been a while now, I guess. This maybe counters my claim that Luis and I are both young. This is 15 years ago, but oh well. This was our first experiment with bosons and fermions. So we were trapping lithium-7 and lithium-6 together in the same trap, and then separately imaging the two isotopes. So on the left, you see an in situ density profile, a column density of lithium-7, and on the right, lithium-6. And this is a temperature about 800 nanokelvin, which corresponds to about the Fermi temperature in this system. So as we go colder, you start to notice that the fermions require a little bit more space. And if you go a little bit colder still to the lowest temperature that we had in this system, which was about a quarter of the Fermi temperature, you can really see the difference between the bosons and the fermions. So now we're low enough that quantum degeneracy matters. The difference here, of course, is Fermi pressure. This is the Pauli principle. This is a thing that Pauli predicted, or Fermi, sorry, the Fermi principle back in 1925, where even at lowest temperature, even at T equals 0, there's still some finite energy in the system. And so since the development of ultracold Fermi gases, there's been a great interest in using these in experiments. First we had bosonic experiments, and now more recently experiments with fermions. The fermions, I think, are particularly interesting because they constitute the building blocks of matter. They're the neutrons, the protons, the electrons. So most of condensed matter physics has to do with Fermi-Dirac particles. Most of nuclear physics has to do with Fermi-Dirac particles. And so there's an opportunity to make those connections. And those opportunities in cold atom physics, and I'm kind of preaching to the choir here. I know that this is one of the centers of this kind of physics, but just in case there are a few new students in the audience, there's all these tunable parameters, interactions, lattice hopping, density, dimensionality, geometry, even spin-orbit interaction, which was really developed here, disorder, and so on. And that enables us to be able to study many different problems of many-body physics. For example, quantum magnetism exotic superconductivity, 1D systems, quantum criticality, disordered systems, topological systems, and so on. So the opportunities here are really great for us to be able to say something significant about many-body physics that people either couldn't say before in condensed matter systems or wouldn't be able to map out in the same level of detail because of this ability to tune these various system parameters. So this is the outline of my talk. That was the introduction. I'll talk about antiferromagnetism with fermions in the Hubbard model. In order to realize this Hubbard model, be able to see antiferromagnetic order, we had to develop some new techniques with optical lattices, and I'll talk about that. All right, so this is kind of a generic motivation for studying strongly correlated or strongly interacting Fermi gases. This is a generic phase diagram of kind of a typical superconductor. This one happens to be a cuprate material, but most of them are very, very similar to this in many respects. In this material, there's a superconducting phase. This is a D-wave order parameter, quantum critical point inside of that. And this is density along this axis, or doping in the case of the real materials. This is the number of holes relative to the number of filled sites in the lattice. And this is temperature, going up to about 300 Kelvin in these materials. And at zero doping, which is 1 particle per lattice site, you can get into this regime where you have antiferromagnetic order. And we're particularly interested, of course, in this D-wave region, this pairing region. But in order to get from here, in order to get to there, we have to get to here. And so this is been a challenge for us in ultracold atom physics to be able to get below this Néel temperature, to be able to see or get close to the Néel temperature where we could see this antiferromagnetic order. All right, so the Hubbard model is kind of, from an atomic physicist's perspective, it's the hydrogen atom of many-body physics. So my thesis advisor was Dan Kleppner, and Dan Kleppner, for those of you who know him, the hydrogen atom was the pinnacle of physics, and it's really, you can demonstrate many, many things in physics from the hydrogen atom, and I think the same is true can be said about in many-body physics about the Hubbard model. The Hubbard model is incredibly simple, an analogy to the hydrogen atom. It has only 2 terms in the Hamiltonian. It's got a kinetic energy term. This T represents hopping, and it has an interaction term where the U is all on-site interactions. The U represents the interaction between 2 particles that are on the same site. So you can see the energy difference between an unoccupied or a singly occupied site and a doubly occupied site. Now, I'm considering just a single band Hubbard model. So here, in order to satisfy the Pauli principle, we can only have 1 particle per spin state per band. And so we're going to ignore higher band effects. That means we have to be sufficiently cold that none of the higher bands are excited. All right, so this is, in actuality, that's the entire model. Now, it seems simple enough, and it is actually easy to write that down. It's a paradigm model of strongly correlated matter because it turns out that this model can't be solved in all generalities. So for arbitrary density and arbitrary interaction strength, we don't know exactly what the solutions of this model are. So we can make some approximations, but the important point that I want to stress is that we don't know whether this model contains the essence of D-wave pairing. We don't know if it contains superconductivity. It's been proposed as kind of the simplest model that contains superconductivity, but we don't know yet. And so this is a real motivation for our community. So the reason why it hasn't been solved is that the basis size, of course, scales exponentially with particle number. And once you get above a few tens of particles, it turns out that this basis size is just too enormous. And even with the fastest digital computers, some realistic size system, has not been solved, and I'm told will not be solved. So it turns out that away from, if we consider just a particular density, which is what we call half filling, which is 1 atom per site, that Hubbard model maps into a Heisenberg antiferromagnet. And this Hamiltonian can be solved exactly. So this is a very special case. This is the special case where we're at half filling at this particular density. And in that case, we can solve it. We find that there's a particular energy scale which is relevant to forming antiferromagnetic order, and that's called the super exchange energy scale. So you can see that it's maybe it's easier if I can get over here. So the super exchange energy scale, the second order term, involves hopping onto one site, interacting with a particle, and then hopping back off of it again. For temperatures that are much higher than this super exchange energy, temperatures that are less than U, the interaction energy, it is known that this Hamiltonian will produce what's called a Mott insulator. So a Mott insulator is different than a standard band insulator that we have in most materials in that it's interaction driven. So it's an example of a strongly correlated phase. It occurs when the temperature is less than U, the interaction strength, and with U over T much bigger than 1. And so it's strongly interacting and the hopping is not that big. Now in that case, you can see over here on this kind of two-dimensional representation of the system that you have exactly 1 atom per site, and the spins are randomly oriented. So in order to see the antiferromagnetism, you have to get to even lower temperatures, which are much lower than this scale where you can see the Mott insulator. So the Mott insulator in ultracold atoms has been mapped out very beautifully in experiments, both at ETH and Tilman Esslinger's group, and by Emanuel Bloch's group in Munich. So about 5-6 years ago, they actually had seen this Mott insulating phase in an ultracold gas of fermions at an optical lattice. Now, an antiferromagnet, if we can get down to this super exchange energy, then you see the difference here. We're still in a Mott insulator, but now we have spin ordering. Now it looks like a checkerboard. Now you have up, down, up, down, up, down, up, down. And you have to get below the spin degeneracy, which is log 2 per particle, in order to be able to go from this Mott insulator to an antiferromagnetic Mott insulator. So this temperature, the Néel temperature, is considerably colder than the transition temperature to the Mott insulator. And so that's the challenge. How do we get to lower temperatures to be able to see this ordered phase? So the state of the art in an optical lattice is in Tilman Esslinger's group, where they've seen nearest neighbor singlet correlations along an anisotropic lattice. So they were made effectively a series of 1D chains, and they are able to get to temperatures that are about 3 times or 4 times this Néel temperature. So, we talk a lot in our field about how we can get to ultra low temperatures, but in reality, when we should really be talking about the ratios of the temperatures that we can get to the Fermi temperature. And the Fermi temperatures in real material are like 10,000 degrees Kelvin. And the Fermi temperatures in our system are like a microkelvin. So there's already, the temperature scale is different by what is that, 10 orders of magnitude. And so in order to get to kind of the similar temperature scale in ultracold atoms, we have to lower the temperature by 10 orders of magnitude. We have to get to some small fraction of a microkelvin, so like nanokelvin. And so this has been a real challenge. This has not been achieved in our community yet, and it really, to be honest, it's been posing a little bit of a roadblock for us to make further progress into seeing the most interesting, strongly correlated phases of matter. So we have to do something. As a community, we have to do something about that. So this is a little bit in more depth what that phase diagram looks like, the transition into the Néel phase. This is for assuming a homogeneous density. So this line is the line that marks out as a function of U over T. It marks out the boundary between antiferromagnetism and a non-magnetically ordered phase. And you can see you need to get entropies that are below about 0.3. So about a half of log 2 in a homogeneous system in order to get into this antiferromagnetic phase. So this is the superexchange energy scale. At very low interaction strengths, the superexchange energy scale crosses over to a different scale, which is exponentially dependent on T over U. And so there's kind of a sweet spot in interaction, which ranges from about 8 to 10 in these units. And so if you get into there, presumably then you maximize the Néel temperature. And relative to the hopping, the Néel temperature is about 0.4 of the hopping energy. It's a little bit different in an inhomogeneous system. In an inhomogeneous system, you can have entropy that varies spatially. So you can have the entropy migrate out to the edges where the density is low and leaving the entropy in the center to be lower. And so for an entropy per particle basis, the entropy that you need to get to cross into this antiferromagnetic phase is considerably higher than it is for the homogeneous case by about a factor of 2. And so this is something to keep in mind. So this is our goal, is to be able to get the entropies that are of order 0.6 or so. So just for reference, this is where the ETH experiment, the current experiment is, with temperatures of about 1 in these units, which you get about a factor of 2.5 above what it needs to be, and entropies that are about also about a factor of 3 or so higher than that are needed to get into the Néel phase. This is my one homage to atomic physics in this entire talk. I'm giving an atomic physics seminar, but this is my only atomic physics I'm going to say. So these are the Zeeman sublevels of lithium-6 atom. So these are energies versus field going up to about 500 Gauss. We utilize these lowest 2 states of the lithium atom, which we call spin up and spin down. They're really just different projections of the nuclear spin, that distinguish them. But nonetheless, they are distinguishable states. And importantly, we can tune their interactions via Feshbach resonance. And so everything I talk about here in terms of being spin up or spin down has to do with these 2 spin states. These are some of the parameters that are relevant in our experiment. We have a few 100,000 atoms. Lattice depths are about 7 recoils. For lithium, a recoil is about 1.5 microkelvin to set your scale. The hopping is something like 0.04 of the recoil. U is about a factor of 10 bigger than that at a scattering length about 250 Bohr. And the superexchange energy scale is a few % of the Fermi energy. So that's the target. All right, so I'm going to digress just a little bit because this is kind of cool. Lithium has been difficult to laser cool through the years because we can't do subdoppler cooling. And I know there are a lot of experts in the audience here who use rubidium, and you get to very low temperatures in rubidium just in a Mott. We can't do that, and we've been envious of that for many, many years. So this is the usual transition that we use, and because of unresolved hyperfine structure in the excited state, we can only get to the Doppler temperature of 100 to 200 microkelvin. But if you use a more narrow transition, this is the 2s to 3p in the UV, it's about a factor of 7 narrower. And because of that, then the Doppler temperature, the Doppler limit, is a little bit colder. And so it potentially is a better starting off point. So in fact, we did the experiment. We made a 323 nanometer source. Actually, we bought one. And we were able to get the temperatures down to 60 microkelvin, whereas our typical temperature with a red Mott is about 300 microkelvin. So that seems pretty good to us. It gave us a much better starting point. We ended up with losing about half our atoms, but we increased the phase space density by about a factor of 10 to about 2 times 10 to the minus 5 in the Mott. If that was all there was, that would be kind of mildly interesting, but it turned out it's better than that even. We found this only after the fact. There's something called a magic wavelength. So the way an optical trap works is that there's a shift in this ground energy level, a light shift due to this off-resonant laser beam. And because the laser beam is red, the light shift goes in the negative direction, and you end up getting a trapping potential. But what usually happens in the usual trap is that at the same time you're shifting the ground level, you're also shifting the upper level. That changes the spectroscopy. And so the cooling doesn't work normally. The Mott cooling would not work in this optical trap. But in very special situations, and this is something that we found from Charles Clark and Mariana Safronova, was that there's a magic wavelength in this transition that happens to be at exactly the wavelength of our optical trap, 1.07 microns. So we were very, very fortunate to find this out. And the advantages of that are that you can now do laser cooling inside this optical trap. And so this is showing that the light shift really is tiny for this spectral line. This is a megawatt per square centimeter of light intensity. And the line shift is only less than a line width, less than a megahertz. And so this is a really huge advantage. And now, instead of increasing our phase space density by a factor of 10, we're actually able to increase our phase space density by about a factor of 1,000. So we can do laser cooling in the trap and get very high phase space densities, which are excellent starting points for doing evaporative cooling. All right, so after about 5 seconds of evaporation, we can get about 5 million atoms at temperatures that are highly degenerate. All right, so that's just a little bit of an aside because I'm particularly excited about that, and I was hoping Charles would be as well. But
it's wonderful.
Yeah, thank you, Charles.
Just putting it up on the internet.
Okay, good. All right, so now I want to talk about this development of this new cooling technique in the optical lattice. So in a trap, evaporative cooling is very, very powerful and a very efficient way of cooling initially, but also maintaining a low temperature. So one thing that happens in traps is that there's a continual heating due to spontaneous emission heating, due to technical noise, fluctuations of the laser intensity, pointing instabilities, and so on. So one way to mitigate that is that you put the chemical potential, you fill up this harmonic trapping volume all the way up to the top, put the chemical potential very close to this continuum edge, and allow hot atoms in the distribution to escape. And in doing so, you're able to get cooling to Fermi gases below about 5% of the Fermi temperature, and that's kind of state of the art. And so in terms of entropy, that turned out to be something like 0.7 kb. So you realize that's already getting very, very close to the entropies that you need from the previous slide that I showed. Now, in a lattice, unfortunately, it doesn't work that way. So in a lattice, the chemical potential sits way down in here. This is the confining envelope of the lattice. This is the lattice sites. The scales are, of course, changed here for illustrative purposes. But you can see that the Maxwell-Boltzmann factor for an atom to escape from the lattice is almost zero. There's almost no evaporation that can happen. And so this is a typical lattice situation. Now what we decided to do was to compensate this harmonic confinement by applying an additional blue detuned laser beam. So this green beam here is not retroreflected, so it doesn't produce a lattice itself. Its only purpose is to superimpose a positive envelope that compensates this attractive envelope of the lattice. And so the result is something like this. And you have a knob now of where you set that chemical potential to this evaporation threshold, and that knob is the intensity of this green light. And that's the idea. So that's the entire concept of this compensated lattice, is that it facilitates atoms that are at the edges of the trap to leave and thereby get colder. All right, so there's actually, it turned out, it's a little bit, there's some other advantages to the compensated lattice. There are three things that we've taken advantage of, one of which is the cooling, but two others. One is gives us a control knob also on density. And the density you've seen is very important to realize the Néel phase. You want a density of 1 atom per site. And also you can flatten the band. And I'll show that in a moment. You can take that harmonic potential and you can reduce its curvature. And so you don't have such an inhomogeneous system. And that's an advantage as well. So the first thing is to control the density. So these are various strengths of the compensation beam. And you can see by tuning the compensation appropriately, we can get into the Mott phase, whereas without compensation or low compensation, it forms a band insulator. And so that's a density control knob that you just simply change that intensity. Secondly, in most lattices, you have strong curvature of the band because of this harmonic confinement. And one thing that our collaborators, Charles Matthew and David Hughes, realized is that you can, with appropriate adjustment of not only the intensity of the beam, but also the size of the compensation beam, you can flatten this band. You can effectively eliminate the chordic part. And this is something that Trey Porto and his group actually realized before us. And it's also that you can eliminate the harmonic part of the confining potential and make it purely chordic. And so that offers another advantage as well. There's a lot of work currently on making potentials that are, very square. And this is not a square potential. In fact, for this kind of work would be a disadvantage because then you'd have to have exactly the right number of atoms to give you exactly 1 atom per site. But it makes the potential with much less curvature, and therefore you can increase the volume over which you create the phase of interest. And then thirdly, it provides cooling. So here's the chemical potential relative to the evaporation threshold. This is relatively small. This is 0 compensation. This is relatively small compensation. This is ideal compensation where we have both a flat band and the chemical potential is very close to the edge. And so by playing with that, you can realize cooling. And that's shown here. So we don't really have a thermometer in the lattice, well we do now, and I'll show that at the end. But a priori, the way we measure the temperatures is to do it in the trap. Then we adiabatically turn on the lattice. We hold for some amount of time. Then we adiabatically turn off the lattice and remeasure the temperature. And all of this is because there's no good thermometer in the lattice. So we measure temperatures to start with that are around 0.05. And as long as we don't hold for too long, the temperature remains pretty low. So this is a hold time of 100 milliseconds in this gray band. And this is a hold time of 700 milliseconds as a function of compensation intensity. And you can see that if you hold without compensation, the 700 milliseconds, the temperature goes from 0.04 to 0.12. And that's because of all those technical sources of heating that I was discussing earlier. So the compensation mitigates that. So we actually don't have good evidence. We don't have evidence that we're doing evaporative cooling in the lattice, except that we know that we can mitigate heating in the lattice. And that's very, very important because that's a limitation in all lattice experiments. All right, so once you get to low temperatures, then you can start looking for some of the interesting phases. These are density distributions that are obtained by doing something called the Abel transform on the column densities that we actually measure. So these are real three-dimensional densities. And at low interaction strength, relatively low interaction strength, we get a band insulator with this particular number of atoms. For a higher interaction strength, it gets closer and closer to a density of 1 at the center until finally when we get to interaction strengths of between 20 and 30, we actually form a Mott insulator with very flat region in here corresponding to the Mott plateau. So the solid lines are actually a theory. These are done by our theoretical collaborators. You may have noticed that there was as many theorists on the title slide as there are experimentalists, and they actually earned their keep in this project. They did all the quantum Monte Carlo, and they did something called the numerical length cluster expansion, which is a high temperature series expansion, and that's what is giving us these density profiles. This is data showing the peak density as a function of number. So as you increase the number, if you don't have a Mott insulator and you increase the number, the density is going to go up. And you can see that here where the interaction strength is relatively small. We increase the number and the central density rises. As we increase that interaction strength, the repulsive interaction, this rise becomes shallower and shallower until eventually at U over T of about 11, it becomes very flat. And this is because of the Mott gap in the excitation spectrum that it becomes incompressible. Incompressibility is related to the change of the density with respect to the chemical potential. So now I want to get to the heart of the experiment. So this is what I really want to tell you about today during this talk. Everything else is kind of a warm-up. So we're taking a page from the condensed matter experimentalists to detect magnetism by doing Bragg scattering. So you probably know about X-ray scattering off of crystals, do X-ray crystallography to measure crystal structure and lattice spacings and so on, or neutron scattering, which is sensitive to spin-sensitive scattering. And then we're doing light scattering, but also in a spin-sensitive way. And so you can see here that if you have antiferromagnetic order, you have certain symmetry planes. You'll see these diagonal lines here. It may be a bit faint, but those diagonal lines are at this 45-degree angle. They correspond to what we call the pi-pi-pi direction in terms of the reciprocal lattice vector. And at this angle, at that particular angle, which we call pi, you get coherent enhancement of the scattered light. And so the scattered light, if you have a detector over there, and it satisfies this Bragg condition that the wave vector in and the wave vector out along this direction are equal to a reciprocal lattice vector q, then you get this coherent enhancement. So this is shown a little bit more schematically here. And again, this is the reciprocal lattice vector, which is sensitive to the antiferromagnetic order. Now we make it spin sensitive by tuning our probe laser in between these two spin up and spin down states that I described earlier. And so you can see that there's going to be a phase shift of pi between the scattered light between spin up and spin down. And so we can be spin sensitive in that way. So here's what the actual apparatus looks like. This is a, without its lid, magnetic field is kind of coming out this cylinder. And we have an input beam that is at this particular angle to the symmetry planes, this lattice, three-dimensional square lattice. This is the pi direction. That corresponds to this direction. And this is some other direction. And the other direction is just for normalization. It's just this another way of making sure that what we're seeing is really due to that particular Bragg angle and not something else. So this is what we call the diffuse scattered light. It's here. In every direction, there's some spontaneous emission. We call that the theta direction. So it turns out that the Bragg scattering actually measures something called the spin structure function. And this is the spin structure function. This is, again, the reciprocal lattice vector. This is the vector to a particular lattice site and to the nth lattice site. And this is the magnetization. And so if you had perfect antiferromagnetic order, this structure factor would be equal to n. Or without this normalization, it would be equal to n squared. If you had perfectly random order, if you had no order in the system, the spin structure factor would be 1. So we expect to measure something between 1 to n. And if you normalize the Bragg scattered signal appropriately, you can actually, the intensity that you measure normalized in that way will give us exactly something between 1 and n. So the atoms are give us this constructive scattering only if they're very well localized on a lattice site. And if the lattice is weak, then there can be some uncertainty in the atom's position on the site, and that weakens a little bit the coherent signal, and that's called the Debye-Waller factor. It's the same thing as the Lamb-Dickey parameter. For those of you who, I know there's some ion trappers in the audience somewhere. And so this is exactly the Lamb-Dickey parameter. It's exactly the same thing. That's R squared, K squared. And in this context, it's called the Debye-Waller factor. So the point is that if we release the atoms from the lattice and then we probe them, they'll lose that ordering. They'll lose that magnetic order very quickly. And the time it takes for an atom to move from one site to another, they'll move to some random place, and we'll no longer see that coherent Bragg signal. And so this provides us a robust way of normalizing the signal after a long time of flight. So we can normalize the intensity of the Bragg signal with 0 time of flight to a long time of flight. This long time of flight is only sensitive to the diffuse scattering, to the spontaneous emission. And that ratio then, if to the extent it's greater than 1, indicates the presence of magnetic order. All right, so this is what we see. So again, this is the spin structure factor. These are the parameters of the lattice. And this is a function of release time from the lattice. We see a peak of 1.3, and after 3 or 4 microseconds, that quickly decays into 1. And there's no adjustable parameters in this theory. This is just a simple fit based on the Debye-Waller factor. Now, if we look at the other direction, this is the theta direction, this is the pi direction, we actually see a suppression. And what's going on there is that there are some doublons here, which this is sensitive to. It doesn't see it. If their site's doubly occupied, actually the scattered signals cancel. Because you have one, the spin up state is emitting out of phase from the spin down. If they're in the same location, then they cancel each other out. And so if you have what are called doublons, sites where there's 2 atoms that are occupying it, that signal will go down, and that's what's going on here. All right, now as a function of interaction strength, so this is interaction strength on this axis, this is U over T, and this is the spin structure factor. You can see it peaks up at around 11 in our units, and then drops appropriately as you go away from that peak, very reminiscent of the Néel temperature that I showed you from the quantum Monte Carlo at the very beginning of the talk. Now we can put the theorists to work, and they get out their quantum Monte Carlo and they get their their numerical link cluster expansion calculations, and they calculate what scattered signal, what the spin structure function is as a function of temperature and different interactions. And so this is a temperature of 1.6 times the hopping, about 1 times the hopping, 0.7, 0.6. And you can see the signal very rapidly is rising. And our data, if you fit it, to this theory, it fits best to this green line. Fits very well to the green line for all the interactions. And by the way, this is averaged over the inhomogeneous distribution. And so this U naught over T naught refers to the center of the cloud. So anyway, that fits to something like 0.5 of T over T of 0.5 with about a 10% uncertainty. And so that's about 40% above the Néel temperature. So even though it's above the transition temperature, there's short-range order that begins to develop before the Néel phase is fully, until you get into the temperature low enough to see the Néel phase, you can still see some magnetic order. And even at very high, relatively high temperatures, you can still see a little bit of that effect. So in summary, we've seen short-range magnetic order. We've seen the order has a range here of about 1 or 2 sites. And so what we have to do, obviously, is to get to lower temperatures. We get down to the Néel temperature, that signal goes from being 1.5 to being something of order n. And so it's really less than a factor of 2. Now, the interesting thing about this, this magnetic order is that we're at the limit of the QMC. So it took them literally months to be able to calculate, these curves. And that's because when you go away from half filling, there is something called a sign problem in the calculation, and requires a humongous amount of computer time to get decent statistics. So we're literally at their limit. So this is a great thermometer now because we can compare it to theory, and we can do thermometry at the 10% level, but we can't, if we go lower than that, then we're on our own. And that's exactly where we want to be. So we want to be beyond what the theorists can do. For so long in the field, we've been, the theorist says, oh yeah, we can calculate that. Oh yeah, we can calculate that. Well, a little bit lower, they won't be able to calculate it. And so that's where we want to be. All right, so all of this is enabled by the compensated lattice, which has given us ability to control density, to flatten the band, and to mitigate heating by doing evaporative cooling in the lattice. And we've just rebuilt our lattice system to be more robust. And give me a second. I'm almost done. To be more robust in order to be able to optimize this evaporation to try to get to even lower temperatures. And we don't really know what the limit is at this point. So we're still there. So the idea is that by getting to lower temperatures, we hope to open up new avenues to be able to study other interesting phases of matter, including perhaps D-wave superconductivity in the Hubbard model, but also some things, for example, the pseudogap phase in the Hubbard model, which is something which is still a bit of a mystery in high TC materials. So let me acknowledge the people who did the work, in particular Pedro Duarte was the lead graduate student, Russ Hart was a postdoc, Ernie Young, Zinzing Liu, and our collaborators, David Hughes, Nandini Trivedi, Richard Skolatar, Teresa Paiva, and Ehsan Katami. Thanks very much.